Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 7.2, Estimating a Population Mean. So in this lecture, we're going to start off by describing the mean point estimate. Then we're going to get into a key question that we need to ask when solving questions about estimating a population mean. We'll introduce a new distribution called the student t-distribution, and we'll look at constructing confidence intervals for means where we both know and don't know the population standard deviation. We'll then finish the lecture talking about sample size calculations. So let's get started. In this lecture, we're going to present methods for using the sample mean to make inferences about the value for the corresponding population mean. Because means are unbiased estimators, the sample mean x bar is the best point estimate for the population mean mu. We can use sample data to construct a confidence interval for estimating the value of a population mean. And there's also correct ways to interpret that confidence interval. We'll get into that in the lecture. We can also determine what sample size we need to have in order to make an estimate of a population mean for a given confidence level. Now, making inferences with the sample mean requires a normal distribution. This means that we either have to have the data normally distributed from the get-go, or we have to use the central limit theorem to say, well, the sample size is greater than 30, so we can use a normal distribution as an approximation for the non-normal distribution. So one of these two requirements has to be met. We got to have normal distribution in our data. There's a key question that we should always ask ourselves when we're asked to use a sample mean to estimate a population mean. The key question is what you see here on the screen. Do you know what the population standard deviation sigma is? This is a yes or no question. So if you answer yes to this question, then you must use a normal distribution and calculate a critical value z-score. If the answer to that question is no, then you need to use a student t-distribution to calculate a critical value t-score. These answers assume that your data is either normally distributed to begin with, or you have a sample size greater than 30. If you don't have a normal distribution and your sample size is less than 30, all bets are off. There's no way you're going to estimate this. So you've got to get more data before you can use the methods here. Now, we are familiar with the normal distribution. We spent a whole chapter talking about it. I should hope we know what the normal distribution is. But what is this student t-distribution? Let's take a look at that. So if a distribution of a population is essentially normal, then the distribution of t-scores forms what's called a student t-distribution for all samples of size n. A student t-distribution is often referred to as simply a t-distribution. We use t-distributions to find critical values denoted by t sub alpha over 2, as opposed to z-scores. These are now t-scores because they come from a different distribution called the student t-distribution. Here's the equation that we use to calculate a t-score. Notice that it's very similar to the equation that we were using to calculate z-scores. The difference is in the denominator. Instead of dividing by the standard deviation, we're actually using the sample deviation divided by the square root of the sample size. So this small adjustment turns a z-score into a t-score. Now, the student t-distribution has a number of different properties. It's actually very different for different sample sizes. It has the same general symmetric bell shape that the standard normal distribution has. but there's a lot more variability with smaller samples. And this is the area in which the t-distribution was actually developed. It's developed by a gentleman who was working for Guinness over in Ireland, and he was looking for ways to do statistical analysis on small samples. He figured it out and published a paper to publish his work so that other people could benefit from it as well. However, being an employee of Guinness, management didn't really want his name out there in case this whole thing flopped on him, because it would come back and hurt the company brand. So he ended up using a pseudonym, and the pseudonym that he chose was the name Student. Hence, the distribution bears the name Student t-distribution and not the name of the actual guy who developed it. That's where that name comes from. So if you're into that sort of if you're into that sort of realm where you like a good glass of Guinness, the next time you have that glass in your hand, I guarantee you're going to think about the student t-distribution, because that's what spawned it. The student t-distribution has a mean of 0, just like the standard normal distribution has a mean of 0. However, the standard deviation for the student t-distribution will vary considerably, unlike the standard normal distribution, which has a fixed standard deviation of 1. For the student t-distribution, the standard deviation will always be greater than 1. It could be 1.1, or it could be 1.5, or it could be 2, or it could be 200. There's a lot of variation with the student t-distribution. And again, that variation comes from needing to have the ability to address the statistics of small sample sizes. Now, the larger you get your sample size, the student t-distribution will get closer and closer to approximating a normal distribution, as you see in the graphic on the right side of your screen. So the more sample size we have, notice how the curve goes up and up and up until it reaches that normal distribution. There's an added concept that we need to understand with the student t-distribution, and that is degrees of freedom. Degrees of freedom for a collection of sample data simply means the number of sample values that can vary after certain restrictions have been imposed on all data values. Typically, the degrees of freedom for most distributions will simply be 1 less than the sample size. There are exceptions to that rule, which we'll get into later in the course. But for right now, just understand that degrees of freedom is simply often abbreviated with the letters DF. So when you see DF, think degrees of freedom. And when you're calculating it, you're just taking 1 less than the sample size. This is what we do for the t-distribution. So take 1 less than the sample size, and that gives you degrees of freedom. When we don't know the population mean, sigma, we can use the t-distribution to construct a confidence interval. So if you're asked to construct a confidence interval for the mean, and you don't know what sigma is, which is very often the case in the real world, you're going to be using a t-distribution to calculate t-scores. Now, critical value t-scores work the same way that critical value z-scores operate. You're just using a different distribution to get the number. That's the only difference. So we're going to calculate our confidence interval just like we did for proportions, only we're going to use the sample mean, which is our point estimate now, instead of the proportion for the sample. We'll still have the same margin of error that we need to calculate, and we're going to do this a little bit differently than we did before for proportions. Remember that our equation for calculating the margin of error for proportions relied on the z-score. Well, in this case, where we don't know what sigma is, we have to use the t-distribution. That means our z-score gets replaced with a t-score. We also note that we're using a sample standard deviation and dividing it by the square root of the sample size. So no more of this p-hat, q-hat business. Now we've got simply the sample standard deviation. Notice that we're using degrees of freedom n-1. Critical values for t-scores can be calculated using either a table or software. There is a t-distribution table in the insert for your textbook, but I suspect that most of you, if not all of you, are going to be using the t-calculator in StatCrunch. Either way, remember to use n-1 degrees of freedom when you're calculating your value. Let's go through the process of how to construct confidence intervals for the mean. It's very similar to the one we already went through for proportions in the previous lecture. First, verify that the required assumptions are satisfied. So the sample must be a simple random sample. The population must be normally distributed. And if the population is not normally distributed, then we have to have a sample size greater than 30, so we can use central limit theorem to come in and say, yes, we can use a normal distribution to approximate. Once our assumptions are satisfied, we need to find our critical value t-score that corresponds to the desired confidence level and n-1 degrees of freedom. We then calculate the margin of error with our margin of error equation, find the values of the lower limit and the upper limit and place them in the general format for the confidence interval, and then we round the limits to 3 significant digits. Let's take a look at an example to illustrate. A common claim is that garlic lowers cholesterol levels. So some people decided to test this claim. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol in milligrams per deciliter have a mean of 0.4 and a standard deviation of 21.0. So now we're asked to use the sample statistics of a sample size of 49, sample mean of 0.4, and sample standard deviation of 21 to construct a 95% confidence interval estimate of the mean net change in LDL cholesterol levels after the garlic treatment. And then we're asked, what does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? Let's look at each of these questions together. First, we need to calculate a t-score. I'm going to show you how to use the t-score table to calculate this, just so you can be familiar with the old school method for doing this. It works the same way as the z-table for calculating a z-score. We just have to remember to include degrees of freedom, which you see there on the left side of the table. We want a 95% confidence interval, so we know that alpha is going to be equal to 0.05. Now, critical value t sub alpha over 2 implies a two-tailed area. Our alpha is being split in half, with one half on the left and the other half on the right. So we need to calculate t alpha over 2. But our alpha is 0.05. So if we have a two-tail column heading, we need to look for 0.05. This is the same as a one-tail column heading for 0.025, which is half of 5%. We don't know what we have up at the top because it's not listed. Generally, when you see that, what you're looking at is a one-tail column heading. So many t-score tables actually have both headings at the top. They have one line that lists the two-tail column headings and then another line that lists the one-tail column headings. Here there's only one line of column headings at the top of our table, so we can assume that we're talking about one-tail column headings. Most t-score tables will actually have a graphic that illustrates whether you're looking at one-tail or two-tail. So we want the column for 0.025. Then the next step that we want to look at is to look at our degrees of freedom. So in our example, we have a sample size of 49. So degrees of freedom is 1 less than 49, which is 48. Now, if you look at the row headings on the left side of the table, you notice there isn't a row heading for 48. So we can interpolate between 40 and 50 to give us the value that we need, which gives us a value of 2.011, or we can simply approximate the value with 50 since 48 is not that far from 50. If we do that, then that means we're looking at this row for 50, and the intersection of the row of interest and the column of interest gives us our t-score value that we want, 2.009. Again, 2.011 is the interpolated value, not that different from 2.09. So let's run through the calculation, and I'll show you how it doesn't make much difference that you're using this approximate value for your t-score. The next step is to calculate the margin of error. So we do that with our margin of error equation. Put in our estimated value for our z-score, 2.009, the sample standard deviation of 21, sample size of 49, punch this out and we get 6.027. If instead we had used the interpolated t-score, we would have gotten a margin of error of 6.033. Again, not all that different from what we calculated. Now we have what we need to construct our confidence interval. So here's the general form. Substitute in what we know. Our sample mean is our point estimate. So 0.4 minus 6.027 on the left plus 6.027 on the right. And out comes negative 5.627 to 6.427. If we used the interpolated value for our t-score, we would have gotten an interval from negative 0.5633 to 6.433. Again, you're not off by all that much. So we're just going to take this, round it to 3 decimal points as our confidence interval. Now, we're 95% confident that the limits of negative 5.6 to 6.4 actually contain the value of our population mean, which is the mean of the changes in LDL cholesterol for the population. So the thing you need to look at now for interpreting the confidence level for the question at hand, because the confidence interval limit contains the value of 0, it is very possible that the mean of the changes of LDL cholesterol is equal to 0. That would suggest that the garlic treatment does not affect LDL cholesterol levels. And thus, it does not appear that the garlic treatment is effective in lowering LDL cholesterol. In order for it to be effective in lowering LDL cholesterol, you would need to have the entirety of your confidence limit, your confidence interval be less than 0. But because 0 is included inside the confidence interval, it's possible that that's a value for the mean of the changes in LDL cholesterol, and therefore we have to conclude there's no statistical evidence for an effect for garlic. So it could be that it affects you, could be that it's not, but there's no statistical evidence that it's going to affect everyone. Now, that's the case where we actually don't know what sigma is. In some very rare instances, we are going to know what the population standard deviation is. And in that case, we need to use a standard normal distribution and a z-score to construct our confidence interval. So we use the same general form, but the way in which we calculate the margin of error is going to be different. This is the minor modification that we need to make for the method for constructing our confidence interval. We're going to use a z-score instead of a t-score to calculate our margin of error. We're going to get these critical value z-scores as we've done previously, either from a table or from software. Let's look at an example to illustrate how this is done. Given the increasing mean weight of men in recent years, we need to redesign boats with an updated mean estimate so they don't become dangerously overloaded. We looked at an instance in class in the last chapter where a boat actually did get overloaded and capsized and sank because there were too many people on board, and there was no knowledge that there were too many people on board because the rating upon which the boat was based was from an assumption made back in 1960. people have been putting on more weight since 1960, so you needed to update the rating on the boat. Let's say we obtain a sample size of 40 and we have a mean weight of 172.55 pounds using a simple random sample of the weights of men. Research from several other sources suggests that the population standard deviation is going to be 26 pounds. So, the first thing we're asked to do is find the best point estimate of the mean weight of the population of all men. Second, construct a 95% confidence interval estimate of the mean weight of all men. And third, what do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels back in 1960? Again, let's tackle these questions individually. So the first one was we were asked to find the best point estimate of the mean weight of the population of all men. Well, this is going to be the sample mean. It's going to be the best point estimate because the mean is an unbiased estimator. So we're just going to take the sample mean as our best point estimate. Now we're asked to construct a 95% confidence interval estimate of the mean weight of all men. So to do this, we're going to have to get some numbers. We want a 95% confidence interval, so that means alpha is going to be 5%. This leads us to a Z-score critical value 1.96. With this value, we can now calculate our margin of error. So pull out our dandy equation, substitute values in, punch this out in our calculator, and we get 8.057. This then we can now substitute into our general form for a confidence interval. So our point estimate, x bar, is going to be 172.55. Our margin of error, 8.057. Subtract on the left, add on the right, and we get the upper and lower limits for our confidence interval, 164.93 to 180.497. This then is our 95% confidence interval for the mean weight of all men, which means that we're 95% confident that the true mean value of the weight of all men lies within this interval. Now, what about the last question we were asked? What do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? Again, we found that our 95% CI is 164 to 180. So based on this confidence interval, it is possible that the mean weight of 166.3 pounds used in 1960 could be the mean weight of men today. It's inside the confidence interval. So it's possible, not saying it's probable, just saying it's possible that that value could still be good. However, the best point estimate of 172.55 pounds suggests that the mean weight of men is now considerably greater than 166.3. We need to reevaluate how we're rating the boats so we don't overload them with passengers. Considering that an underestimate of the mean weight of men could result in lives lost through overloaded boats and aircraft, these results strongly suggest that additional data should be collected. Again, the 166 is inside the confidence interval. So statistically, we don't have the evidence that says that it needs a change. But because the point estimate that we're using is greater than that value, we need to say, okay, we need to take a look at this. It's potential that more data will give us a different confidence interval, and that confidence interval that we get with more data will exclude the assumption that was made back in 1960. So getting more data is always a good thing. Here in this case, because that point estimate is greater than the assumption for the weight that was used back in 1960, yeah, it's suggesting we really should get some more data so that we can be sure that that value does not need to be changed. As we saw from the previous example that we looked at in class back in chapter 6, yeah, that value actually does need to be changed. So in this case, collecting more data is a very good thing to do. Let's look at another example involving the depths of earthquakes. So here we have a dot plot showing 50 earthquake depth measurements, which have a mean value of 9.8 and a standard deviation of 5.01. What is the 95% confidence interval estimate for the population mean? Well, first, the key question is, do we know what the population standard deviation sigma is? I'll give you a moment to answer the question. Okay, hopefully you read the problem statement over again and saw that the population standard deviation is not given to us. Therefore, we do not know what sigma is. That means that we need to use the t-distribution when we're calculating our margin of error. So whenever a problem statement does not tell you whether or not sigma is known, just go ahead and assume that it's unknown and proceed to use the t-distribution for calculating the margin of error. Now, we can go old school and we can run through the table again, but I think it's much easier to use StatCrunch. So let me show you how this is done. So inside StatCrunch, you want to go to Stat and then T-Stats, one sample with summary. This is the option that we're going to be using for actually calculating the confidence interval itself. If we wanted to go a little bit old school and calculate the margin of error by hand, we could go back up to the top here and click on the calculator option and then get our student T calculator out and calculate that critical value T-score and then use that to calculate the margin of error. Alternatively, we can just go down here to T-stat and use the functionality inside StatCrunch to go ahead and calculate the entire confidence interval itself. Since we don't have actual data, we have a dot plot, but we don't have the actual data points that was used to make the dot plot. So that's going to be that we're just going to use the summary statistics that were given in the problem statement. That means go ahead and just select with summary. Now, in the option window that appear, go ahead and select your settings. Notice up here at the top, you're asked for the sample mean, sample standard deviation, and sample size. Those values were listed in the problem statement, so go ahead and throw those in. And then make sure that you've got this radio button selected for confidence interval for mu, so that you get a confidence interval out in your results window. The level needs to be entered in as a decimal. So in this case, we wanted a 95% confidence level, so we would enter in 0.95 into that field. Once we've done this, we press compute down at the bottom, and out pops this lovely little results window, and lo and behold, here's our upper limit and lower limit for our confidence interval. We can then round to 3 decimal places, or however many we're asked to round to, and there's our answer for our 95% confidence limit. Let's look at another problem where we actually do have data. What is the 99% confidence interval for the mean brain volume in cubic centimeters based on this sample of 10 brain volumes? And then you're given 10 numbers. Assume that sigma equals 125.95 cubic centimeters. So now the key question, do we know what the population standard deviation is? In this case, the answer is yes. They gave that to us right at the end of the problem statement. So now we know we need to use the standard normal distribution and not the t-distribution. So instead of going to t-stats there in StatCrunch, I'm going to go to z-stats. So first I need to enter in my values into StatCrunch and find the summary stats. Or I could just enter in the values themselves and then select with data instead of with summary, and then select a column where the data is actually located. If I do the summary stats and then put the summary stats in, I'm going to get pretty much the same answer. So here's my summary stats. Now I'm going to use the Z-stat option in StatCrunch to find my 99% confidence limit. And here's what I get when I do that. So here's my lower limit, here's my upper limit. There's my 99% confidence interval for the mean brain volume based on those 10 brain volumes in our sample. Given that typical brain volumes typically vary between 950 and 1800 cubic centimeters, do these values from our 99% confidence interval appear typical? I'll give you a moment to decide. Well, I hope you answered yes, because the entire CI that we calculated is within the range of these typical values. So because the entire CI is composed of typical values, yeah, the values from our CI do appear to be typical. Let's talk about calculating sample size. We had a similar conversation about this when we were talking about estimating confidence intervals for population proportions. Now let's do the same thing for population means. Here's our sample size equation. Notice it's slightly different from the one that we were using for sample size for proportions. That's to be expected since the mean and the proportion are two different values. But this is the equation that we're going to use to calculate our minimum sample size that we need. Now, as before, we're always going to round up to the next whole number when we get our final answer out. Now, there's one thing that we need to know about this equation, and that is that it requires that we know sigma. I mean, look at it. It's like one of the inputs here for our equation. So we have to know what sigma is. But most of the time, we don't know what sigma is. So that means we're going to have to take one of three options. The first option we have is to use the range rule of thumb to estimate the value of sigma. Second option that we have is to collect the first set of data values and then to use the sample standard deviation as an estimate for the population standard deviation. This can be a little tricky because, remember, standard deviation is a biased estimator. So it doesn't tend to the sample standard deviation is going not to tend to target the population standard deviation. However, with this option, what we do is we make a first estimate and then we collect more data. So then we keep making newer and newer estimates of our standard deviation in order to estimate the sample size. The last option that we have is to use the results of an earlier study to estimate a value for sigma. This tends to be the method that's most commonly used in the real world. It's easier just to take value from another study and use it as our estimate than it is to do one of the other two options. Let's look at an example where this could be used. So assume we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Well, first, we recognize that we want a 95% confidence level. That means alpha is going to be 5%, and that means that our critical value z-score is going to be 1.96. We take our equation for calculating minimum sample size, and now we're going to plug in what we know. But first, we need to know what sigma is. We weren't given anything from that in the problem statement. So let's go and look up a previous study, and we find one that suggests that sigma is 15. So that's the value we're going to use for our calculation. When you're working problems in your homework assignment, for example, you have to be given that information. You're not going to be expected to go scrounging around the internet for a value for sigma. That's not the way this is going to work. So you're going to have to be given something. Typically, there will be a statement somewhere there in your problem statement that says something to the effect of, there's a previous study that suggests sigma is equal to yada, yada, yada. So then just go ahead and put yada, yada, yada into your equation. Here in this example, let's put the values that we have. So 1.96 for our critical value z-score. 15 is what we're taking from the previous study for a population standard deviation. And we want to get within 3 IQ points of the population mean. So 3 becomes the value for E. Notice this is not 0.03. These are not percentage points. These are IQ points. So because these are not percentage points, you're going to put the actual number that they specify in the problem statement in for your margin of error. In this case, 3. Punch all this out on your calculator, and out comes 96.04, which of course we round up to the next nearest whole number. So we need a minimum sample size of 97 in order to construct a 95% confidence limit that will place the sample mean within 3 IQ points of the population mean. That brings us to the end of this lecture. If you have any questions, you know what you need to do. Otherwise, I will see you in class or the next video. Thanks for watching.